Good afternoon, everyone. For today's session, we are going to start in 2 minutes. I welcome Jinesh sir for this session. Hello, sir.
Hello, sir. Am I audible?
Yes, sir. You're audible.
Okay.
And so in today's session, we are going to see review of Turing machines, classical computational complexities, and time and distance complexity details. So sir sir is from Presidency University, Bangalore, and over to you, sir. So I hope take the session. Yes, sir. You can continue.
Okay, sir. Is it visible?
Yes, sir. It is visible.
Okay.
And participants might be writing their queries in the chat box. So
Okay.
meanwhile, whenever you
Okay.
feel free, you can just. Thank you, sir.
Okay. So, good afternoon, all. We'll be starting with the theoretical computation. So, today's plan will be try to understand what is different types of automata machine. So that is a basic for all algorithm design. So for that, we'll be going through what is language and what is the connection between languages and automata. Then, specifically in automata, Turing machines, and how we can connect these Turing machines for algorithm design. And again, this algorithm design, once we are designing the algorithm, we'll be knowing we need to evaluate the algorithm based on the performance, okay, whether it is performing better or not. So how we can use this Turing machine for algorithm performance, and what is the relation between this algorithm performance and the Turing machines through Turing thesis, and again how we can use this Turing machine for designing quantum machines, so that once we are having Turing machine for quantum machine, obviously quantum related algorithms also possible. Okay, we'll go through all these. So most of you may study all these things, or you may be teaching also in your course. So we'll just refresh the things in another perspective, and we'll try to connect with the quantum systems. Okay, so first we'll be starting with the languages. So basically, any language will have alphabets, then a set of rules and regulations, uh, how to use the alphabets to make the strings. Okay, so for what purpose we are using languages? Languages we are using for communication between two different entities. Okay, so mostly these two entities may not be at the same time. See, for example, script, whatever we are using languages, Hindi, English, or whatever, we are having alphabet set. And always remember, this will be a predefined alphabet set. Okay, it cannot be like a unlimited or infinite set of alphabet set, or predefined alphabet set only we will use. Okay, and then, there is a difference between alphabet and the character. Okay, so alphabet means always we will be having some kind of information connected with these characters. See, you can see on the screen letter, okay, few letters in different languages. So first you can see, okay, I'll just use pen highlighting this. Okay, so first letter, it is in Tamil. Next you can see in Kannada. Then you can see in Hindi. Then you can see in Malayalam. Okay, all letters who are knowing these languages, while seeing the picture, you will be making the sound A. Okay, that means you are putting information that is to make the sound while seeing the picture. Okay, so there is a connection between like a language and information. So languages, especially scripts, alphabets. Okay, then alphabet we are using to represent the information for a future purpose, or few who are coming later, or in after 1,000 years or so, you may be communicating same information. Okay, so similarly, another set of letters I kept here, like a letter K in different languages. You can see which of the language you don't know, you may be feeling it is like a picture. Okay, since it is not having any specific uh, meaning on that. Oh, okay, so then formally we can say a language contains a set of strings. That strings will be formed by a sequence of letters. Okay, so these letters here again alphabet. Okay, then strings can be considered valid if and only if it follows the rules of the language. So what it means, simply if you are writing some sequence of letters, you will not get a valid or meaningful sentence in a specific language. For getting a meaningful sentence in the language, we should follow specific rules and regulations. Okay, means the combinations or permutation what you are using to create the string, you should follow the regulations. Okay, then that example you can see here, ABC. Okay, both all three letters are from English language. But the thing is, whenever you are using in the order A, B, C, it is not valid. Means we cannot find out the specific meaning on this. But the same thing, if you are rearranging like a CAB, that's a specific meaning. Okay, right. See here, why? Because it happens here because we are following the rules of the language, English language, so that we are getting the meaningful sentence or string. Okay, so in this string, okay, in this slide, what we have seen, what is a language? Okay, so always remember, language will have a predefined finite set of alphabets, and each of the alphabet will have a specific meaning. That is, alphabet will be a picture or character, uh, which having embedded information in it. If you are not embedding information in it, it cannot read as alphabet. Okay, then why? Okay, this one as a computer science faculties will be knowing, whenever you are using English alphabet, okay, English characters or alphabets in any programming language. In programming language, we are not calling it as alphabet, we are calling it as character, because there we are just using the picture. Okay, so the letter A, B, and all, it is not using as its own meaning in which is in the English language. There in a programming language, the meaning will be different. And that is the what are the compiler we are using. It may be define your letter with some other meaning. So we are and then each situation to situation also it may vary. Okay, that's why we are calling it as character in programming language. Just be aware about this, or please remember this one, while, especially while reading papers about theoretical computer science. Okay, so in this slide you can see how a computation happens. Okay, generally, uh, what are the digital computers we are using now? This is a scenario. Okay, so you can see there's a microprocessor unit, that is CPU, and it is connected with the temporary memory, and the temporary memory will have a set of instructions. Normally that set of instruction, what we are calling it as like a program. Okay, then the processing unit will be taking the instructions, and it is getting information from other locations, maybe input memory and output memory. Okay, and this will be executing with the set of values. Okay, until we are getting the final result. Okay, so an automata theory is nothing. It is a study of abstract machines and automata. Okay, so what are the computational problems we are facing, and how to use an automata concept to solve those problems. Okay, so the in here I'm just trying to connect with the digital systems, or how digital computers are executing the program, and how we can connect this with the automata concept. Okay, this we will have a look into this. So down we can see program memory. There we are having the program. So normally, whenever we are typing a C program, let us say take a C program, we are typing the program and saving it as a file. Okay, then that file will be compiling and we are getting an exe file. So that is a in the exe file, what we are having, a set of instructions to be done by the computer to get a specific task or predefined task. Okay, so that is in the program memory. So normally whenever we are trying to execute the program, the file will be loaded into memory. Then CPU will be executing the instructions one by one, and in the instruction, what are the values required that we are taking. So here in this example, I want to find out x cube. Okay, so in the top we can see the function f of x equal to x cube. This is my task. I want to find out this x cube. Okay, so whatever the value I am giving, I need to find out cube of that. So in normal mathematics, we know how to find out x to the power of 3. X to the power of 3 is x times x times x. Okay, then that we are taking, okay, x times x times x. Okay, so for doing this, what we'll do, we'll multiply first to, okay, x will be assigning with a value and it will be multiplying 2 times, and that result, okay, that result will be multiplying with the same number one more time, so that we are getting x cube. That is what you can see here. Okay, first we are multiplying 2 times 2, so the result will be getting, that result will be multiplying with the 2. Okay, so that we are getting 8. Okay, and this 8 will be reflecting on the output memory. Okay, so you are having input memory. So normally while executing the program, we will say that we are initializing a variable or declaring a variable. That variable will be storing in our primary memory, and later it will be taken to the register, okay, input register, and from the register CPU will take the value, do the operations, and the result will be reflecting on another register, and from the register will reflect it to the uh, specific function or the variable where to store, and it may be displayed on the screen or something. Okay, so that is how in normal systems it is working, means in the digital system, what are the architecture we are following, it is following this sequence. Okay, so here what is happening, we are giving the information to the system. That means we are communicating to the system. Okay, so for communicating, we are writing the program. That means we need to communicate to the system. There are two entities are there. Okay, as programmer and the computer. So for communication, we require language. Okay, then the language should be suitable for both of us, both of the system as well as the programmer. That means both entities should understand each other, so that the programmer is not using his own language and the computer is not using its own language. So the mutually understandable language using. Okay, and then using that language we are giving instruction to the system or commands to the system. That is what through program we are doing. Okay, and then here in the primary memory we are loading the file, means your program file, and we are reading the instructions one by one. Okay, means one instruction at a time we are reading and we are executing. Okay, or we, in the sense, a CPU is reading from the program memory. Okay, instruction by instruction it is reading, and each instruction it is going to execute. That means the execution will be in a sequential order. Okay, so we can consider like the program we are keeping in a sequential memory, and the program is reading instruction by instruction from one end to another end, and parallelly we are executing. So we can consider it is like a ribbon, okay, tape ribbon, and there we are putting instructions. Okay, I1, I2, suppose I3, I4, like that, and you start reading from left, first instruction and towards the right side, and whenever we are reading each instruction, some kind of changes are happening to the system. Okay, whenever we are reading first instruction, the status of the system may be S1, and after reading S1 your status may change, and by default you are going to shift to next location, then your system status may be S2. Okay, system status become S2. Again, with the S2 you are reading next instruction I2, then your status may change to S3 and you may go for next instruction. Okay, so this is a normal. If you are imagine in this way, you can match your computation, your system computation with this idea. Okay, this is a concept. So each of the status of the system we are representing like a state of the machine. We are assuming that we are having a machine, and that machine is able to read input from an input tape. Okay, so this is input tape. Assume that you are having an input tape, and this tape can keep alphabet, or because we are keeping the language, even your program also we are using the program to communicate with the system or computer, so that the program itself we are considering like a language. So the language in our case language, I mean, here in the in case of program. Alphabet. This character sequence we can consider like a string, means by definition the string. Okay, in any programming language the string is collection of alphabets. Okay, that means see in the previous slide we have seen cab. Okay, it is CAB. That means a collection of alphabets. Similarly here, the sequence of input we consider like a collection of alphabet. That means a string. Okay, so I hope you are able to imagine you are giving a program. That program we are considering like a string, and the string you are keeping in a tape. Okay, and you are reading the string from the first alphabet to last alphabet. That means whenever you are reading a string, you are reading from leftmost alphabet to rightmost alphabet. Okay, then if the string is meaningful to the system, system will understand the meaning, so that we will get the output. If the system is not understanding meaning of your string, or that means your program, you will not get proper output from the system. Okay, that is what in normal finite automatons are happening. You are assuming that you are having a system with input tape, you are giving input string on the tape, and the system is able to read from the leftmost character towards right side, and while doing by reading the alphabets or input alphabet, your machine is subjected to change the states. Okay, that means each state changes will be subjected to the input as well as the present state. Okay, then based on the state changes are happening. And towards the end of the string, if your machine is able to reach a final or output state, we can say it is the given string is meaningful or valid. Okay, this idea we can use for designing the systems or designing the algorithms with a proper output. Okay, so this is just an introduction, and this we'll get into more details about different types of automata. Okay, so there are different types of automata. Generally, we'll say finite automata, that is in next we are having another type of automata, that is push down automata. So there we are having a physical property like extra memory, that is stack. Okay, again there it will have deterministic push down automata as well as non-deterministic push down automata. Okay, then we are having bounded machines as tour machine. Okay, last we'll see tour machine, again deterministic tour machine and the non-deterministic tour machine, and another type of tour machine, that is bounded machines. Okay, bounded automata or bounded automata machines. So there also this it is same or similar to tour machine, but there is a restriction in the memory representation. Okay, so these are the four types of automata machines. We will see each one in detail, how we can represent those things and how it is related to our languages. Okay, so I'll just repeat one more time. Okay, so we have seen what is a language. We have seen language consists of strings formed by uh, various combinations of the alphabet, which is a predefined set of alphabet in the language by following a specific rules and regulations in the language. The specific rules and regulations known as grammar for the language. Okay. Then we have seen what is a automata machine concept. So how here in this slide we have seen how we can connect the automata concept with the modern digital systems. With a small example, like if we are writing the program will be in the program memory, that is in your program file, and the program file will be reading instruction by instruction, and for executing the instruction you may require some kind of input, and those inputs will be taken by the system, and based on the execution the system status may change. Okay, so we just try to connect all this with the automata concepts. Now we have seen what are the different types of automata available or kinds of automata, that is finite automata, infinite finite automata. There are two different types, that is deterministic finite automata and the non-deterministic finite automata. Another type is push down automata, then bounded machines and tour machines. Okay, in tour machine the main uh, property is it is having random access memory, and the expressive power of all these automata, tour machine is having the highest expressive power. Okay, so that means most of the languages will be can be represented by using Turing machine. That means most of the programs or what are the problems available or solvable with the digital systems, all can be represented using our Turing machine. Okay. Then least expressive power is with the finite machines. Finite automata will not have that much. Okay, very limited type of languages can be represented by finite automata. So the languages which can be represented by finite automata, that is known as regular languages. Okay, then languages which is represented by push-down automata is known as context-free languages. And then we are having recursive languages and recursively enumerable languages for represented by Turing machine, and the context sensitive languages can be represented by bounded machines. Okay, this is a case. So here recursive languages and recursively enumerable languages will be the superset compared to all. Okay, then subset of that will be context free languages. Okay, and the subset of context free languages will be uh, this one. Sorry, context sensitive languages. Sorry. Regular language, then subset is context sensitive language. Then we are having context free language. Okay, then we will have uh, regular language. Recursive language and recursive enumerable language is a superset. Then context sensitive language, then its subset will be context free languages, then its subset will be regular languages. This is a hierarchy actually. Okay, that means if you are able to design a Turing machine, you will be able to uh, make a machine to accept a specific recursive enumerable language and the recursive languages. And most of the programming languages having the property of recursive languages means we are using recursion. Okay, so if you want to make a algorithm, we can analyze the algorithm by using by design the Turing machine for the algorithm and analyze the Turing machine. So whatever we are analyzing with respect to Turing machine, it will be equal to the analysis of your actual uh, algorithm. Okay, so now we'll see finite automata in little detail. Again, the machine concept. Okay, you will not have any temporary memory, so you will have one input. You will be giving input to the machine. Your the machine will be processing, and you are getting an output. Okay, so we are using quintuple representation. Quintuple means quin means five. Okay, QUIN. Quin, the word quin, the meaning is five, means we are using five tuples or five entities to represent the machine. So this we will connect with the our machine concepts. Okay, so Q sigma delta Q0 F. So here Q is a set of states. So in the previous slide we have seen we are having a machine. Okay, the machine concept like an input type, and input type we are reading from the left to right, character by character, and there is a chance of getting different states in the machine or different status in the machine. So that is what here the state. Okay, set of state. So how many states are possible for a machine? So all those states together will represent as state Q. Okay, a set Q, capital letter Q here. Then we are having set of input alphabet. Okay, so that means uh, I said if we are considering digital computer system, we are giving the program, and while executing the program, what is happening in the primary memory, your program file will be loading, and the program file will be reading instruction by instruction or line by line. Okay, so one instruction at a time. So similarly, we have a concept of finite machine. We have an input type. Okay, so in the input type, we are putting alphabets. Suppose you are giving 0, 1, 1, 0, 0, etc. Okay. So you are going to read from left to right, means at a time you are reading one alphabet. That is our theoretical concept. In the actual situation, while reading the program file, the system or CPU will be reading one instruction at a time. Okay, it is all exactly matching with our automata concept. That is how automata machines can be representing, can be used to represent the systems. Okay, the computing systems. So here, how many alphabets you are using in our language? That is what sigma. Okay, that is set of alphabets what we are using in your language. In case of programs, how many instructions are using in your program? Normally, any programming language it will have a specific number of instructions. That is keywords. Normally, okay, we can just match with the keyword. Otherwise, if you are taking microprocessor programs, we will be using that microprocessor instruction set. So that instruction set will be always limited. Means it cannot be uh, like an infinite set of instructions. We'll be having a specific number of sets. Okay. So here we can say this in what we are considering for a set of input alphabet. Okay, this is like a set of instructions what we are using. Each of the instruction we are considering like a one alphabet. Now we can see here delta. Delta, what it means is transition function. So here we consider there is a function which is controlling the state transitions. Okay, so in the example we have seen, your system is reading input, and based on the situation or state of the machine and what input you are giving, your machine state will change. Okay, so that change of the state, that which state it is changing, that change will be controlled by a function. That function we are considering as transition function of automata. So here delta we are considering as transition function. Okay, then here you can see another one, q0. Q0 initial state. So initial state means whenever the machine start reading, what is the state of the machine. Okay, so Q0, it is representing initial state of the machine. Then we can see a final state or acceptance state, F. So one example we'll consider for this, then it will be easy to understand. Suppose we are taking example washing machine. Initially the washing machine is switched off, nothing is there, okay, no power supply. We can consider like it is a sleeping mode. On the sleeping mode, if we are giving power switch on or power on, then what will happen? The system become active. Then the status of the system is changing from sleeping to active. Okay. So for that state change, what we are giving power on. Okay, means some input is getting to the system. Then on the power on mode, you can select different functions, that is predefined function, the washing machine. It can be a rinsing, it can be washing or whatever. Okay. Then once you are selecting the function, your system will be going through different states. For example, if you are selecting the washing mode, what will happen? System will fill the water. Okay, then it will start rinsing, means it will rotate the cloth inside the drum. Then a specific amount of time it will rinse. Okay, then it will stop. Okay, then usually if it is an automatic, fully automatic washing machine, after rinsing, what it will do? It will go for drying. Okay, rinse then dry. For drying, what will do? It will remove the water. It will remove the water. First, it will remove the water. Then it will rotate very with a high speed for a specific amount of time. After that, again, it will fill the water. Like this cycle will continue for a certain amount of time. Again, it will after we can decide which is required, whether you require wet cloth or dry cloth. Okay, that is known as this acceptance stage. So initially it was empty. Okay, water was not there, system was not power on, it was empty situation. Then we are getting putting power on. Then a system is giving a chance to choose a function, predefined function. That function will have a sequence or a specific sequence of operations, a specific sequence of operation. Okay, then after that, after the specific sequence of operation, what you are expecting from the system, that we are defining as acceptance state or final state. Okay, so in case of washing machine design, we can decide we require a dry cloth set. Okay, what are the cloth we are loading should be dry and get back. Otherwise, we can decide like we don't want a dry cloth. We need only cloth. So just after washing, you can remove the water and keep it ready instead of going for uh, high speed dryer. Okay, that also there. So that flexibility will be with the designer. So this finite automata, not only this deterministic or not finite automata, any automata concepts or automata system, we can use for any specific system design. Okay, normally any project can be started with the finite automata design. Okay, so that then this input each time we have seen the state changes are happening because of some certain type of inputs. That input we are considering like input alphabets. Okay, so then with respect to each state we are going to read the input symbol. Okay, the input symbol already loaded into the tape, that is input to memory. Then alpha character by character we are reading. Okay, with respect to the stage, and with each stage, okay, each stage on a specific input, what is the next stage, we are going to take a decision. Okay, that decision making will be happening through the control function. That control function we are defining as delta. Okay, so we have the state, suppose it is S1, we have a set of states. So what are the possible state in the machine we are defining, S1, S2, S3, something, etc. Okay, and it cannot be infinite, it should be finite. And at present, which state you are reading, okay, with the which state you are reading the input. And based on that, that is input state, present state and input symbol, what should be the next state? We are going to take a decision. Okay, this decision making we are defining as a function that is represented as transition function. So I hope you are getting the idea, delta of S1. So I will be representing this delta as the function name. Okay. In parenthesis, we are writing S1 comma 0 is equal to S2. That means at present you are reading the input 0 on the state S1. So that the machine will be transferring to another state S2. Okay. Then when once you are reading an input, by default your read head will be changing to next location or okay, moving to right side. Okay, automatically it will go to right side. So we will not bother about the uh, direction of movement in this case. So if I am writing a transition function delta of s comma 0 is equal to s2, I can write like s1, then to S2 it is changing. Okay, on input 0. This is the idea. Okay, this is how we are representing the function. We have the transition function delta of S1 comma 0 equal to S2. That means your machine was in the state S1. On reading input 0, new state has come as S2. That's the meaning. Now we will see two types of specifically they define two specific states here: initial state and acceptance state. Initial state means from where your machine start reading or start processing the input language or input string. Okay, and the final or acceptance state means the acceptable or expected state of the machine for the customer or for the designer. See, for example, our washing machine, we start reading the power button, then going through different activities. At last, if the customer or system is defined for a dry output, okay, so the after drying it will be stopping, so it will rotate, remove the water, and it will go for dryer. Then after dryer it will stop, or the system will give a stop action. That is expectation. Okay, so that expected state will define as acceptance state of the automata. I hope we have done all 5 tuples in the finite machine, and you should be aware about all this meaning, or exactly what is the meaning of this. And the same thing will be using for all other automata concepts. Okay, little small variations in this. Okay, now we'll see how to represent this machine. Once you are having the machine with us, how to represent, we'll see. Okay, so basically there are 3 different methods to represent this automated machine. First one is state diagram. You can see on the right side, up, right side corner. Okay, state diagram. It is like a directed graph in data structure or algorithm or graph theory somewhere, and we have studied about graphs. So we will have node and connected nodes with the directed arrows. Okay, so automata machines we are representing using this connected nodes. Okay, then we can see a state table. Okay, a state transition table is also known as state transition table. Tran State transition table. And we have another method is quintuple representation or using the state transition function. That is what the left side you can see, quintuple representation, or okay, with the transition functions. So we'll see, we'll take one example and we'll represent the same concept of same system using all 3 methods. These are the basic 3 methods, and all type of automata we are going to use same concepts, same type of representations. And specifically for tour machine also we are using same thing. And this tour machine is very important for us for algorithm design and analysis. Okay, it can be in a digital or classical system, or it can be in quantum systems. Okay, so I'll just take an example that same or washing machine example take. Initially, washing machine power was not on, so that means it is in the sleeping mode. I just represent the sleeping mode as S. Then we are giving power button. Okay, power supply. So once power supply is enter into the system will become active. In the active mode, based on the selection, your machine will change it into different modes. Okay. For example, if you are selecting washing as an option, then wash, okay, button you are pressing. Or suppose you are making dryer option. Okay. So it will change to another situation. Okay. Then based on that, state will change. So suppose here wash, okay, then active 1 will say, in active 2 it is a dryer mode or something like that. Then if you are selecting active mode, what we need to do, we need to fill the water. Okay, so in active mode automatically it will fill the water, then it has to rotate. Okay, so after filling the water, so start filling the water and it will be in the active mode itself. Okay, in the washing mode, and fill the water. Okay, filling the water. So filling water is okay, that activity is happening. Then once the sensor sense the like it is going to overflow, then it will stop, and then automatically it will go for washing. Okay, or rotating with okay, rotation. Okay, so some kind of interrupt will be happening for that. Suppose I'm reading an input interrupt R, so system will start rotating. Then after some time, the system will go for uh, drying the water. Okay, drain out the water, and it will go for rotating with high speed. Okay, that is rinsing. Again, this cycle will continue. Okay, so suppose here I have another input, interrupt 1 and interrupt 2. Then it is okay. Then based on the expectation, this cycle may repeat 2 or 3 times. Then you can fix the final stage. Okay, suppose after rotation, uh, okay, suppose after rotation, I don't want to drain out the water. I can stop there. Otherwise, I can run the dryer and I can stop. Suppose I am taking that option. Okay, so A2 I'm fixing as final state or acceptance stage. My acceptance is I will get wash. Okay, the machine will wash and it will rotate for okay high speed rotation swing for that is action. So this will repeat for a specific amount of time or the same thing. Okay, then it will stop. Okay, so assume this is our machine to represent your uh, washing machine system. Then in your program, you will be writing, suppose you are loading a program to run this machine. Then suppose in the instruction P is for power on, W for washing the system, okay, washing, okay, to change the mode to washing mode. Then in the washing mode, you will be filling water for some time, okay. Then you will be having rotation, okay, rotating the drum for some time. Then you will be getting interrupt 1. Then after that, you will be having swing. Then you will be having I2. Again, you will be having fill. Then again, you will have rotation. Then I1. Then if it is stopping, you are in which state we can decide. Okay, so we can identify this. So here what is happening, you are having a sequence of instruction, right? So each of the instruction you can see like a character in the string. So this program, it is like a string. Okay, so from where you are reading, your system will start from the power button. So the state, okay, then always the power button on is possible only for the state where it is sleeping. So you are by, okay, in our design case, sleeping mode is the start state of the machine. So you have start reading from S. Then with the S, if you are reading P, what is happening? Your okay, your state will change it to A. Then on A, if you are reading A, what is happening? Your state will change it to A1. On A, you are reading fill. Okay, fill water. Then your input will okay. Uh, your state will be A1 itself. Means you are keep on filling the water, but you will not change the mode. Then in that, if you are reading A R, what will happen? Your mode will change to R0. In R0, R1 means sorry, I1 means your state will change to A2. Okay. Then in A2 you are reading I2, so your change will be state will become A1. Again you are reading R, so again you will reach R0. Again R0 R, you are reaching A2. Then you are reading I1. Sorry. Okay. Sorry. A2. A2 means A1. A1 fill is A1 itself. Sorry. Okay. Here A1 fill is A1 itself. In A1 R, you are reaching R0. Okay. Then in R0, you are reading I1, you are reaching A2. So you are not getting any instruction. That means you are reaching end of the string. Okay. So your state is A2. Then in this situation, if you are reaching the final state or acceptance state, you can say the input sequence is acceptable by the machine. Okay, what it means, your system you designed for washing clothes in using your washing machine. and you are giving a sequence of input or sequence of instructions so that you are getting the expected output. Whether your given input is providing expected output or not, that is what we are getting here. If you are reaching the final state or acceptance state A2, okay, by end of the instruction set, by that means end of the program, you are reaching your expected output. That means the given instruction set is suitable for your system. Okay, then what is this? A sequence of alphabet or sequence of instruction we are calling a sequence of alphabet. That means string, input string. So now we will say the input string what I given here, it is acceptable by the designer machine. I hope you are getting the idea. Okay, this is how we will be using automata systems, okay, for reading a language and finding out whether it is acceptable by the system or not. Okay, so now we will see how to represent this same machine using table. This is what I have drawn here. This is graphical representation or directed graph representation or transition state chart diagram. It is also known as transition state chart diagram. So you will be representing all the set of states as A, A1, R0 as well as A2. Okay. Then you are what are the inputs? In our case, we are having P, W, like different. Okay. Then with respect to each stage, will then R, I1, I2, D. All these are our instruction alphabet, input alphabets. Okay. Then which is the start state of the S. So the start state and final state will be representing specifically like this. S is the start state and the A2 the final state will represent with the star symbol. Okay. Then with respect to each input, which state transition is happening, that will represent here. S, P is A. So with respect to P, I will write A here. S and W and those things are all not defined. Okay, so all are undefined states. Then with the A, W, it is A1, and with the A, D, it is A2. So like this. Okay, A1 F is A1, A1 F is A1 itself. Then A1 R is R0. A1 R is R0. Okay, so like this we will be filling the table. This table is known as transition table representation of the machine, automata machine. Okay, I'm not filling all. Okay, so first one is transition state chart diagram or transition diagram. Transition diagram. Okay, then next we can see here transition table or state table. Okay, then another method to represent the same thing is quintuple representation. So according to this design, we are having total 5 states. All the set of states will be representing as Q. Okay, capital letter Q. Within the set symbol, we'll write all the state names. S, comma, A, comma, A1, comma, A2, comma, R0. These are the states defined for this machine, specific machine. Then what are the alphabets? Defined alphabets used for the machine. Okay, so here in our case it is P, W, fill. Okay, this R, I1, I2, then D, R. D also already written. So set of all inputs, defined inputs for the machine that we will be writing within the set symbol. Okay. Then we need to represent which is a start symbol of the machine. Okay, that is what here they in the previous slide you have seen Q0. In our case, yes, always any automata machine can be finite automata, push on automata, tour machine, whatever. In any machine, we will have only single start state, that is Q0. Okay, that's why we are representing within with the state name without any set symbol. But we can have multiple final states or multiple acceptance state for any machine. So always final state will be representing within the set symbol. In our case, our final state is A2, so I am representing A2 within the set symbol. Okay. Then now four contents are over. Now fifth one. Fifth one is transition function or state transitions. Okay. So that we are representing using delta. So here delta of S comma P, state S and input to P. What is the next state? Here A. So S comma P is equal to A. I can write. Okay. Then delta of A comma W, I can write A1. Okay. So delta of A1, if I'm writing comma fill, that means, okay, if it is fill, that is equal to A1 itself, means same state. Okay.
Going to Gundari.
So,
Sir, kindly take 5 minutes break so that we can change the YouTube session.
sir,
Sir, kindly take 5 minutes break so that we can change the YouTube session.
okay, okay, okay. Okay, okay. So what time all of we can come back? Now 3 o'clock. Can you came back by 3:05?
Yes, sir, we will start 3-5.
Okay, okay.